Good evening, everybody, and welcome to the Carolan Cymru revision sessions. The session this evening will focus on
capacitors.
Part of the A2 physics syllabus, and will be presented by Mrs. Jane Owen of e-sgol Penglais School in Aberystwyth. The session will last around 45 minutes, where Mrs. Owen will run through the relevant content with you. If you have any questions during the session, please use the Q&A section and we will do our best to answer. You'll see that there's a hyperlink in the Q&A section already, and if you're happy to leave your details, we would love to keep in touch with you and let you know about events in the future. You can click on that link at any time during tonight's session. The session will be recorded, and the recording and all resources will be uploaded to the e-sgol website under the Carolan Cymru tab. So thank you, Mrs. Owen, over to you.
Okay, good evening all, and yes, I'm going to talk about capacitors and revise everything in capacitors and capacitance. Okay, so let's have a look at capacitance. Capacitance can be defined as the charge stored across the plates divided by the potential difference across the plates. So we have a capacitor, we charge it up with a PD, and the charge stored on the capacitor plates will be dependent on the PD that's supplied to the circuit and the capacitance of the plates to be able to hold the charge. So this side will be negative charge stored, and then it will be the opposite positive charge on the opposing plate. So we can define capacitance in terms of that equation as long as you state what each of those terms are. So Q is the charge stored and V is the potential difference across the plates. Now, capacitance is measured in farad. So we say in the little brackets there, farad, F, and we define a farad in terms of the other units. So 1 farad equals 1 coulomb per unit volt. Okay, so it's how much 1 farad is the capacitance of a plate, the ability of the two metal plates to store the charge per unit voltage supplied across those plates. Okay, so we can change the capacitance of a plate, and the most easiest and very common question how to improve the capacitance is quite simply to add a dielectric. And by adding a dielectric, it's basically a better insulator than air in between the two plates, so that if we are able to apply a voltage across the plates, then we can push an electron to be pushed onto one plate, and then that will induce a positive charge on the opposing plate, so that the electron that was pushed away from the opposing plate will travel around. So you've effectively got one electron from this plate going all the way around and pushed around by the potential difference onto the other plate. So we can improve the ability to do that by adding a dielectric. And with a dielectric, we have a permittivity, a relative permittivity, and that can increase the permittivity of free space. So let's go back a little bit. Capacitance is given by permittivity of free space times by the cross-sectional area of the plates that you put the charge on. So that's cross-sectional area, all right, of the plates, divided by the distance between the plates. So we can increase the capacitance, yes, by adding a dielectric. And if we add a dielectric, we add kind of a relative permittivity, which is a number usually bigger than 1 that is multiplied by the permittivity of free space. So the permittivity of free space is the capacitance per, well, the amount of farads per meter of air or of free space, and that's given as a constant, 8.85 times 10 to the minus 12. And that's given to you in your data booklets that you can refer to. So the relative permittivity tends to be a number greater than 1, a number greater than 1. And so that it's multiplying the effect of the permittivity of free space. And so therefore it means you can store more charge for your unit voltage. But we could also increase the area, but that's not practical. But how you see the capacitance is usually they're in a cylinder. And what that means is that you have kind of like one plate, which is positive, curled around with another plate, which is negative, and that's how they get a bigger surface area, by coiling up into a cylinder. We can also decrease the distance between the plates to increase the capacitance. So if we decrease the distance, okay, and make it smaller, then that means the capacitance will increase. If we increase the area, the plates that can store the charge, I like to do it in class in terms of size of buckets. If I have a bigger bucket, I can store more charge. I can store more ping pong balls. If I have a smaller bucket, I can store less charge. Okay, and that gives you an idea of a bigger area, bigger capacitance. Okay, all right, so moving on. If you have, we can work out the capacitance by measuring the charge stored with the voltage, and we get a straight line, and that gradient there will be given by Q over V, which is our capacitance. Now, something else that we can do, and this is all good graph skills, and this, can be applied to anything in physics. There's two things that we always look at for a graph, and that's the gradient, and here it gives us the capacitance, but we can also look at the area underneath the graph. So if we have a look at the area underneath the graph, that gives us the energy or the work done trying to put the charge onto the plate. So the work done is the same as energy stored of the charge, is equal in this case to half QV. All right, but we know that the gradient is given by C, the capacitance, so that Q can also be written as CV. All right, so just rearranging this gradient equation. So if we've got the charge as CV, we can actually pop it in for the charge here to get the work done or the energy stored, and sometimes we call it the internal energy U, is equal to half CV times by V. So that gives us half CV squared. All right, now what do we mean voltage? And I'll come back to this first initial diagram. If you've got a lower voltage across the capacitor plates, then it is much and you've got no charge stored initially. So if I show it to you here, actually I'll bring it across here. So this is my battery. Okay, and I'm charging up a capacitor plate. I don't need a lot of energy to move the first electron around and onto that plate because there's nothing to oppose it. Okay, and that's going to push an electron off and around. So effectively, I've moved one electron off one plate and onto the other. So the work to do this is not a lot when there's no charge onto that plate. But now we put kind of like more charge onto that plate. All right, and that means that we've got deficiency of negative electrons on the opposite plate. Remember that charge can't cross the capacitor plate at all. It's a dielectric, it's an insulator. So you've only got the charge being stored and separated onto the plates. So whatever charge you've got here, you've got the opposing charge on this side. Because if you get rid of an electron and induce a positive charge there by repelling an electron, it leaves a positive charge which is equal and opposite to the other plate. So now if I've got a little bit higher voltage, I'm trying to put an electron onto this plate. It's much harder to do it. So I need more energy, I need more work, I need a higher voltage, I need a higher push to get that charge onto the plate in order to separate those charges. So it makes sense that the bigger the voltage, then the more work I have to do to get the charge onto that plate. Now, there are other equations that you can use instead of half CV squared, because I can substitute for Q, which is what I've done. I can also substitute for V. So using this equation again, V is Q over C. And I can put that in for the voltage. So energy equals half QV. And so if I substitute for V, I get half Q times Q over C, and I've got half Q squared over C. Okay, so that's another way that I can look at this. So I can use the this equation, half QV. I can use this one, half CV squared, and I can use this one, half Q squared over C, is the work done or the energy stored on the capacitor. So I've got three different equations that I can be using. Okay, and it just depends what you're given. All right, and it just depends what you've been asked to work out in the previous part. Okay, let's go to looking at capacitors in parallel and in series. Okay, so I'll set up a capacitor in parallel first, and let's call it a little C1. It's a little capacitance, medium capacitance, and a big capacitance. And I'm just going to do it by showing kind of like big surface area to show the difference between them. The distance should be the same, okay? Right, so I've got, now, what do we know about all of those capacitors? We know that the potential difference supplied across all of these are identical. Now, I really want to try and find the colors draw. Yeah, I just need a little bit of color for you. Now I'm going to go with, so on this side is all positively charged. So let's say that this is the positive side. All of this side is positive. I just want to show to you that it's all got the same. And I'll go black. This side, I'm going to set it as 0 volts. Okay, so all of this is 0 volts all the way around. So you can see here that V1 across the capacitor plate V1, V2 and V3 is the same as the supply voltage supplied to the circuit, because you can see the difference where the supply is between the the positive and negative of the supply, it's a certain voltage, and it's between the red and the black. And you've got between the red and the black for C1, for C2, for C3, which means that the voltage difference between the plates on C1, C2 and C3 is the same as the supply. So the voltage across the total, all right, and that's supplied to the circuit, is equal to the voltage across each of the capacitors. Now that might come in handy a little bit later on. Now, capacitance. What would be the total capacitance? Now, let's see our equation for capacitance. Our equation for capacitance is Q divided by V. Okay, now the charge stored across voltage 1 is given by Q1. Now, because you've got a small area, you've only got a small charge that can be stored there. Whereas for capacitor 2, you've got a little bit more charge stored because the area is a little bit bigger. Capacitor 3, you've got an even bigger charge stored because you've got an even bigger surface area. All right, so the total charge supplied divided by the V supply will be given by whatever the charge stored on 1 plus the charge stored on 2 plus the charge stored on 3. And it's like having a big bucket of charge, a medium bucket of charge, and a little bucket of charge, and you add all of those together, and that is the total charge that you will have. Okay, divided by V1, V2, V3. Okay, right, what am I doing? So C total equals now, so that means that in a parallel arrangement, as we have here, where all the capacitors are in parallel with one another, that the C total is given by whatever the capacitance of plate 1 plus whatever the capacitance of plate 2 plus whatever the capacitance of plate 3. And that makes sense because whatever the charge is, you know, is the total sum of all of the charges on all of the plates. And that means that the total capacitance in parallel, you can just add them up. But in series, it's a little bit different. The story is a little bit different. So let's have a look in series. It's the opposite to adding resistors in parallel and series. So if we have got a row now of capacitors in series, so we've got small one, small area, medium area, and very large area for our different capacitors. We've got C1, we've got C2, and we've got C3. Let's make it so that it's a little bit bigger so that you can get the idea clearly. Right, now we've got to look at it slightly differently. I'm just going to change into red. If we have a voltage supplied here, that will give an electron enough energy to go all the way around onto this plate. So we have one electron here. That will induce an electron to kind of be repelled away and be pushed onto this plate 2. So we're left with one negative here and one positive here because an electron has been pushed away. So we've got this one will be negatively charged, and this will induce a positive charge here because an electron will be pushed away onto our other capacitor, and then this one will literally push an electron around, leaving this plate negative and this plate positive. Well, in a sense, if I do this, and I'm going to take a different color, green, and take all of this out of the kind of equation, basically what I've got is that voltage supply will push one electron onto one plate, and effectively one electron will leave on this plate. So it doesn't matter what the size of those capacitor plates are, the charge will be identical on each of those plates. So Q1, Q2 and Q3 will be identical, and that will equal the total charge in the on the capacitor plates. Because if C3 holds a certain charge, then C2 will hold the same charge because it's had to be repelled from C3, and C1 will hold exactly the same charge. And that's probably your key point to have to try and remember. In parallel, the voltage is the same. In series, the charge is the same across each of the capacitor plates. So let's have a look at it then. Now let's have a look at the voltage. I'm going to change colour. So let's have a look at how the voltage is going to be. Now we know in series that the voltage kind of is shared. We can't say splits up. We have to say it's shared between the three plates. So the voltage across the supply is equal to the voltage across, say, capacitor 1 plus the voltage across capacitor 2 plus the voltage across capacitor 3. So I'm going to put V1. Notice I haven't a V2, okay, and V3. Notice I haven't assigned whether they're big or large yet. We'll have a look at how big they will be in a minute, all right? So now let's go back to our equation. Q equals CV, so C equals Q over V. So Q over C. So the voltage of the supply is Q total divided by the capacitance total of the series circuit. And that is because we've got C equals Q divided by V. So we just rearrange that, voltage equals Q over C. Now that is equal to Q1 over C1 plus Q2 over C2 plus Q3 over C3, but because the Q total is the same as the charge stored on plate 1, as the charge stored on plate 2, as charge stored on plate 3, that will all cancel out. And you're left with 1 over C total equals 1 over C1 plus 1 over C2 plus 1 over C3. All right, now, okay, so this means like resistors in a parallel circuit, the effect of adding more resistors will be actually to reduce the resistance. So the effect of having more capacitors in a series, the effect is to reduce the overall capacitance in the circuit. Now, let's just have a look at how the voltage would be. Now, you've got the same charge, Q1, on the capacitor plate C1, but you've got less room to spread the charge out. So the voltage for capacitor on the voltage across the capacitor 1 will be much bigger. So in fact, this will be V1. Why? Because the charges are very, very close together, so the potential difference between the plates will be much higher. Whereas the charge stored across the capacitor 3 is exactly the same. but that charge is able to spread itself out along the surface area of the plate. So instead of, for example, having, 4 charges all squashed up on C1 to give a high voltage, now on C3, the charges are able to all spread out all over the plate. And therefore, the potential difference across the plates is much smaller. So in fact, all right, the voltage across V3 would be the smallest voltage, because the charge can spread out over a bigger surface area, so the potential difference between the plates will be a lot smaller. All right, and so it's probably a different way around to intuitively what you would expect. Now, I just want to have a look at this equation before I go on. This 1 over C total is 1 over C. Let's just take it for 2 capacitors in parallel. All right, now you just got to be able to remember to add in terms of fractions. All right, but you must keep it, kind of like the right, kind of like as a reciprocal until you've added the 2 together. So we've got to have a common denominator, so C1, C2, all right, times C1 by C2, or 1 times by C2 for the top bit, add, now, times 1 times C1 for the top bit on the other side, and then we've got the sum over the multiple. But then, now we've got it together, we can turn it upside down. So C total, okay, now we can turn them both upside down, is equal to the multiple divided by the sum. Now, it doesn't actually work very like this with 3, but you can work it out using reciprocals on your calculator, but you've just got to remember to turn it the right way up at the end. And if you get something that is far too small, then you've forgotten to turn it upside down. You've forgotten to press the 1 over to get it out. But you can remember, you don't have to remember this equation here. You can remember that C total for 2 capacitors is the multiple over the sum. All right, and that will work every time. If you want it for 3, C1, C2. If you want it for 3, then it will be the C1, C2, C3 multiple over C1, C2. Hold on, no. Let me go back. C1, C2 plus C2, C3 plus C3, C1. Hopefully, you won't need it for this, and then actually, let me just think about it. It's C1, C2, C3. Yes, I am right. I was right the first time round. So let's just cross that out, not to confuse you. It's like this: C1, C2, C3, the multiple over. Now, C1, C2 plus C2, C3 plus C3, C1. And that is actually for 3 capacitors. But to be honest, if you remember the reciprocal and you'll be given that one, and you can remember just the 2 of them, that's all you're going to need. You're really not going to need to go to 3. Okay, so now can we go to the exponentials, because in A2 physics, they really love to have this idea of charging a capacitor or discharging a capacitor. So for example, when you're discharging a capacitor and you've got a current or an ammeter in the circuit, and you've got current with time, you have basically, if you are discharging, you will have a maximum current flowing, and then it will decay exponentially. Okay, and if you are measuring the charge stored on the capacitor Q with respect to T, there will be a maximum flow of charge off, and then again an exponential decay. And if you have a voltmeter across the capacitor plates, then that voltage will be a maximum, and then it will discharge to a 0, and we say an exponential decay. And of course comes with this the exponential equations. So I equals I naught e to the minus t over RC. Okay, and it follows through this exponential equation to describe that graphical form. So I naught is given by the original current flowing. So if you imagine that you've got a capacitor which has been charged up so that it's fully charged up, and then you switch that capacitor into a discharging circuit with, say, a resistor R in the circuit for the capacitor plate to discharge through, all right, that's the circuit that we have got. So it's called a discharging circuit, all right, as it is shown here, because I've charged up the capacitor to a certain voltage, I've stored all of my charge on it, and then I have using it to discharge it through a resistor. Now, if I charged up my capacitor one way and then I discharge it, so for example, let me show you. If I charge it up, the same capacitor that I've got there, I will have a negative on this plate, so negative charge here and positive charge here. Now, if I now put, so that's the charging circuit. And the charging circuit will look slightly different to all of this. It will look like that, as opposed to the discharging circuits that you can see there, the 3 of them there. Now, in the charging circuit, when I put my fully charged capacitor into the discharging circuit, now what you've got is you've got this as negative here and you've got this as positive here. Can you see that in the charging circuit that the charge will be flowing in one direction, whereas now the discharging circuit will be in the opposite direction, if you like, because it goes from the negative charge and it will want to neutralize and make it all neutral by taking the negative charge through the resistor and around onto the positive plate. And then when it's fully discharged, then you've got equal numbers of positive and negative charges on both plates. All right. And that's when you are down onto, you know, asymptotically approaching 0. So this equation relates kind of your discharging circuit, and with time t you can work out what your current is depending on the size of the capacitor that's in your circuit and the amount of resistance resisting the flow of the charge off the capacitor plates. So clearly here, if you've got a big capacitor here, you're able to hold more charge, and therefore it's going to take a lot longer to discharge through the resistor. So the higher the capacitance and the higher the resistance, then the time it takes to discharge is going to increase. Now that, and just coming back a little bit, the resistance in the circuit, if I increase the resistance in the circuit, then it's more difficult for the charge to actually be flowing around to the other plate because there's more resistance to the flow of that charge. So we call this product capacitance times resistance is the time constant. So we call this, and we say that roughly 4 to 5 time constants, all right, is the time it takes to discharge. okay, time to discharge. Now, can I prove this to you? Let's have a look. Capacitance times resistance. And now we tend to do the time constant like this, little tau. All right, so that means it's measured in seconds. Okay, now capacitance is equal to charge divided by voltage, but charge is given in coulombs. This is why I always put units in brackets, because you can see that capacitance that's in farads is going to be confused with charge stored in coulombs. All right, so Q is the charge, and current equals the rate of flow of charge. So charge can be written as a current times by time. So charge equals current times by time. So let's play around a little bit with these units. So charge equals current times time over voltage. Now, and resistance is given by ohms. Okay, so can I do anything here? I think I can. So you know that resistance is equal to voltage divided by current. So if we have the product of capacitance times by resistance, the capacitance is given by current amps, seconds, I'll put it in brackets so that I've got the units in brackets, over volts. Okay, so that's all of the capacitance times by the resistance. Now the resistance is given by voltage divided by amps. Okay, and now look, I can cancel. So cancel the volts, cancel the amps, and I'm left with the seconds. So that means that the product of capacitance times resistance for discharging circuit gives us the time constant. And this is why it appears in that equation, that logarithmic equation. So I equals I naught e to the minus t over RC. So this time here is the thing that changes. So time divided by the number of time constants will give you kind of like a factor of time constants in that time t. So let me be a little bit more specific. All right. I'm going to I naught, okay, with time. So I naught after a certain time of RC, which is the time constant, then I naught drops by a factor of E, 2.3. Okay, so that coincides with one time constant. So that's I naught divided by 2.3, i.e. I naught divided by E. Because look, I equals I naught E to the minus T over RC, but minus RC over RC is I naught, I equals I naught E to the minus 1, which is I equals I naught over E. So after one time constant, the original current reduces down by a factor of E. After another time constant, i.e. the same time, all right, so that now I go to two time constants, then guess what? I naught gets reduced down to E squared, because T is 2RC. So 2RC divided by RC gives you I naught over E squared. So I equals I naught e to the minus 2 RC over RC. That cancels with that. And then you'll get I equals I naught e to the minus 2. So I equals I naught e over squared, e squared. And so on until eventually you get to 3 or 4 or 5 time constants, and it's reduced exponentially down to very, very close to 0. So the significance is in that equation of that logarithmic equation is that in the same time interval, the initial current, it reduces down by the same factor. All right. Now, let's just look at all 3 of those equations. So there's 3 of them that you have to learn. Don't worry, they pop up in other topics as well. Radioactivity, nuclear decay, they all come up, these logarithmics. So if you can understand it here, you can apply it to elsewhere. E to the minus T over RC, and then comes, and I'll go to black I think now, V equals V naught, the original voltage across the original PD across the plates, e to the minus T over RC, and also Q equals Q naught e to the minus T over RC. Now we'll look at something else, but you need to kind of like look at like the time it reduces by half, say, or the amount, because very often they don't give you the I or the I naught. They'll just say it reduces down by a factor of 50%. So if, say, one of these, let's take our original one and reduce by 50%. They haven't told you what I or I naught is, but I, the final amount, is going to be 50% of what it was before. All right, so that would be I divided by 2. All right, I naught, and can you see that these cancel out to give you e to minus T over RC? So you've got half equals e to the minus T over RC. Now you can log it. So log of a half equals minus T over RC. So therefore, you can bring the negative over and this log changes. So log 2 equals T over RC. We know what RC is, so we can work out RC times by log 2 gives you the time it takes to halve the either the current or the voltage or the amount of charge. Now, just to finish, I should recap, but there's one more thing that I want to show you. Now, you've got this equation, I equals I naught e to the minus T over RC. They love you trying to get that into a form that physicists like, and that is a straight line relationship. And what you're going to have to do, you're going to have to log it, and you're going to have to natural log it because you've got an e there. So natural log I equals natural log I naught minus T over RC. Okay, so that's logging it. And then you have to relate that to y equals mx plus c. So what are you going to plot against what? You can log I on the y-axis, and on the x-axis, you will plot t. It means that your y-intercept will be equivalent to log I naught, okay, is equal to the y-intercept c, and your gradient, notice, will be negative, and your gradient here, I'll put here the gradient m, is equal to -1 over RC. So if you have the resistance or you have the capacitance and you've got to find the other one, you can, let's say we want to find the capacitance in the circuit, so it's C equals -1 over R times by, say, the gradient M. So M here is the gradient dy by dx, okay? And finally, to find what A naught is from the y-intercept, you will have to do e to the c equals I naught. Okay, I think I ought to come to a stop here. And thank you for listening.
Okay, great. Thank you, Mrs. Owen. Well, I hope you all found today's session useful. Now there will be 3 more sessions, 3 more Physics A2 sessions. So we hope to see you next time. Goodbye.